I feel confident talking about vectors because I know you all have experienced them before pretty much, and they're fairly straightforward in the way that we're introducing. All right, vectors, remember, represent magnitude and direction. And when I think magnitude and direction, I'm thinking strength. I want to know how strong something is. I want to know how large it is. Well, that's going to be best represented in a vector, even though I can kind of do the same thing with coordinates. Especially as you saw in Calc BC, how vectors can be parametric equations. And things like, imagine placing a parametric equation into the various aspects or components of a vector. All of a sudden you have this powerful idea that my vector could be changing. Right? For any given vector, I have a head and a tail. Right? This is the tail, this is the head. And imagine these heads are leaving an imprint. My function is changing, my t value is varying. And if I smooth out this shape, all of a sudden, imagine collecting an infinite number of vector heads as they recalculate and move across the space. All of a sudden, I'm left with a smooth curve or an arc. And imagine, that's how 3D printers work. 3D printers are understanding one little dot at a time, one little triangle, one little head of a vector at a time. So imagine parametrizing something like this, right? This Pringle shape. Well, if I could write an equation that parametrizes this whole shape, as you can see, almost in the grooves reflecting off of the light, right? I can find the channels and paths that would trace across this surface both width, length, and height to print it, as long as I put limits on my t. And so all sorts of good things come from vectors. We have a whole chapter dedicated to it called Vector Calculus. It's important in motion because, again, not only does it show that motion over time, it can show us magnitude and direction, things like that. A lot of our functions get broken down into components of just x, y, and z, I, j, k, and so we just love vectors in this course. One thing we'd like to look at is the direction of a vector, right? If I put this thing out here, I know that I would have my two components, my x component along the bottom, my y component along the top, and I'd have some angle that it makes with the x-axis in standard position. I see this is rise and run, and that's where this tangent is coming from, and that's where a calculator might help you get your finished answer here. I'll admit, this is one of the few places that we do like to use calculators in this course, just because we might like that exact answer, but if you came out with something like tangent of 1 over rad 3, I would accept that as an answer on a test most of the time. Pretty much. All right, let's talk about magnitude. Magnitude tells me the strength. It tells me how strong it is. And hopefully when you're looking at this magnitude equation, you're also seeing a little bit of distance formula, right? I can see how far away things are based on the change in x, so the change in y, or in 3D, the change in x, y, and z. So over here it's talking about finding the vector that represents, or find the magnitude and the vector that represents the space between these two. Well, I'm just looking at the change in x, y, z. So if I'm trying to write this vector out, I would get my change in x. It goes down 6. My change in y goes up 6. My change in z goes down 10. And that order matters a lot. That order matters a lot because that order tells me, hey, whether my tail is here, my head is there, or my head is there and my tail, my tail is here and my head is there. Imagine the difference in tracing this shape if I went based off of the tail or the head. It would come out significantly different, so knowing A to B versus B to A makes a large difference. When I go to find this magnitude, I'm just going to shortcut it, right? 6 squared plus 6 squared plus 10 squared, and I'd get something like rad 172. All right, if you're a good math student and you know that things simplify, you might be looking at that saying, well, I know 4 goes into it, and you'd be right. 2 rad 43. That one's a little obscure, but I believe in you to find it. All right, I'm thinking about this one. It's saying find the angle between the x-axis and the terminal point on this vector. So it's asking me to do just this. Hey, I have a vector. There's a terminal point at the head. Find the angle between the x-axis and that point. So again, I could even use that same kind of picture where I'm somewhere in the first quadrant. I'm heading out. I have this coordinate where I know my base is 4 rad 3 and my height is 4. I'm dropping in altitude, so I'm making a right angle, and I'm looking for this angle. And I know that I can use tangent to compare the rise and run to find the slope and to find the angle at which this makes with the axis. So the tangent of my angle is rise over run. And I would use my tan inverse. I would simplify this even. Let's look at it. Tangent is 1 over rad 3. Well, hopefully you remember a little bit of your trig. If not, we have a trig review in review 3, so that'll help you a little bit here. But I know that this is a low-flying slope. I see the rad 3. I know that is a unit circle relationship. I know that I'm going to get 30, or pi over 6, as my answer. Okay, well, what would happen if I took this coordinate and I pulled it, if you can't tell, I'm moving up, 16 spaces in the sky? Well, what angle would it make from this point down to the ground? And so you really have to consider, what shape is it making, right? From up here, back down and across, straight up, back down and across, straight up, back down and across. It's just another triangle. Oh, you're saying, but how do I know information about this triangle? Like, I'm definitely looking for this blue theta. When I pull this up, what do I know about this triangle? Well, I know it has a height of 16 because I pulled it 16 spaces up, but I definitely need one of these others to help me out. And what I hope that you recognize is that this corner is sitting here. This right angle is right here, being pulled up 16 spaces. So this base is this base here. This hypotenuse is the same as this base of the triangle over there. So if I want to find this so I can make that final trig relationship, I just have to use a little bit of distance formula, or Pythagorean theorem, to find that third side. That third side looks like this, right? C squared equals the change in x squared plus the change in y squared. Here I'd have 16 times 3 plus 16, gets 64, and 8 is my final answer. And so I know my base is 8. I know that hypotenuse was 8. And so now when I'm setting up this tangent relationship, it goes 8 here, then it goes 16 up. And I'm looking at this right triangle that I've laid flat over here. Again, I have a tangent relationship, OA, which just means tangent inverse of 2 is my final answer. And I'll admit, this is one of those places that I would be so happy if you stopped here. You do not have to take this any further. We prefer exact answers to calculator answers, but if you must, you could double check that my angle is 63.44 degrees. Again, in this course, we're heavily going to rely on radians. We're heavily going to rely on exact solutions, so I don't feel a strong pull to do more than this. I know you see this box of text at the bottom, and you might want to pass it by, but here we are. Thinking of vector addition, right? I could have two vectors, one that looks like this A and one that looks like this B. Well, A plus B is that result of the action. Here, this is A plus B. But I can also do B plus A, and hopefully I should end up at the same place. So I did B plus A, I would end up at the same place. It shows a little bit of the commutative property here. Even something like A minus B. A little bit of visual work here as you work through on some of these things. And these are straightforward. Even something like the scalar multiplier, this is just going to be distributing into the parentheses, or into the vector, you might think. Over here, let's talk about parallel vectors. Let's think. Two vectors would be parallel if they looked like this. 1, 2, 3. Or 3, 6, 9. Right, because they're heading, they got the same rise and run. Even though it's 3D, I'll still call it rise and run for the sake of your knowledge. Right, it's still changing at the same rate in each direction. So there must be something that's true about them. Some parent function, some mother vector that would allow me to reference this whole family of vectors. And this gets more important as we get into equations of planes and things like that. But it would be called the unit vector. That's what it says here. They would share the same unit vector. Well, how do I find the unit vector? I take any vector and I divide by its magnitude. And notice the symbol here, it changes to a little hat. Instead of the vector line, it turns into a little hat. U hat always has a magnitude of 1. That's its best quality, a length of 1, a magnitude of 1. And that might not matter as much today, but if we go into the future and talking about parametrizing surfaces, or if we talk about normalizing functions like curve length, I need it to be in terms of unit vectors, because unit vectors will make sure that I have no stretch or shrink to account for, because everything will be on a scale of 1. I don't want to talk too much more in the future. That's just something to remember for a later day. It's been 11 minutes on the front page. Let's go, folks. I, J, K are my standard unit vectors. Those are the 3 directions. The x direction, the y direction, and the z direction can always be referenced through I, J, K. We can take a set of vectors and break it down into individual components and write it as an equation, which you'll see on the back. Even something like this, 1, 2, 3, this would be I plus 2j plus 3k. That's simple, right? It just allows us different ways, different writing conventions for these things. Show that a plus b equals b plus a when I have these. Straightforward, folks, right? The a plus b would have 4 plus 8, 6 plus 2. That'd be 12, comma 8. B plus a would look like this. 8 plus 4, 2 plus 6. And you know that because addition is commutative, you would end up in the same place. We saw it visually, but we can also see it here. Now, as you saw, when I add 2 vectors together, it makes a really unique shape. And we'll dig into this more as we go into 12.3 and 12.4 especially. But let me show you one of these, and then I'll kind of back out and leave it to you to consider. Right? These are pretty large vectors, so I'm going to count by 2, 4, 6, 8. The fact that I'm going to have one that goes over 4, 1, 2, 3. This is A. This is going to be B. And that B plus A, or A plus B, is the resultant vector here. Whereas if I did B first, and A second, I would end up at the same place, but again, I would have B plus A. And this is like a vector parallelogram rule. There's some interesting relationships that happen in here. But what I'd ask you to consider is, how do I find the area of this? Right? It's spanned by these vectors. It's formed by these vectors. This should be pretty straightforward. The parallelogram area formula is just base times height. How could you find the base and height from here? How would you know where to launch off? How would you know what the right angle is, the right slope is for you to make an altitude? How could you measure the altitude between 2 points? I know you could find the base easily by finding the magnitude of B. But how could you find the area of this? And I'll just kind of leave that one to you guys to consider. We'll revisit that in 12.4, or you can brute force it now a little bit. Find the unit vector for this thing. Again, the unit vector would be this, V, divided by the magnitude of V. So I need to find the magnitude if I have any hope, and to find that magnitude, that would be this square root. 2 squared plus 1 squared plus 2 squared. Again, doing some shortcuts there, ignoring the fact that I have negatives because they're getting squared. I get the square root of 9, which is 3. So that unit vector, that's V hat, looks like this. 2/3, negative 1/3, and negative 2/3. And again, I could write that in IJK form. 2/3 I minus 1/3 J minus 2/3 K. pretty straightforward in that. All right, onwards it says find the scalar multiplier that shows their parallel. Because again, for two things to be parallel, I should be able to multiply them by some number and find the other vector. Well, if I'm trying to figure out what multiplier moves between these, I already found it. It's that magnitude. Just a good conceptual question here that if c is 3, that means 3 times v hat makes the regular vector v. Not rocket science, just simple things to consider. And this last one is just a problem I want you to think about for a minute. Right, there's a weight hanging from the ceiling, which I've now poorly drawn. There's a weight hanging from the ceiling, and it makes a 50-degree angle on this side and a 32-degree angle on that side. Let's try that again. That's a much better drawing, and it makes a lot more sense, and it fits what we're talking about, where T1 is the tension force over here, and T2 is the tension force over here. Ultimately, this is making some kind of triangle, where each one of these vectors have, right, vertical components and horizontal components. And so I'm trying to find, if this is a 100-pound weight hanging down, how could I possibly find what those forces are? How could I find what T1 is, and how could I find what T2 is? They're being held in stasis. They're being held in stasis. So you have to consider that, well, it's not quite moving, right? You're thinking. Okay, let's consider first. Let's look at the I components of each. Well, the I component here, this is cosine. So the cosine of 50 will give me the I components. Will give me the I components on this side and the cosine of 32 on this side. Component. Well, this system has any pull that happens this way also happens this way. So the resultant force in the I direction ends up being 0. And so that means my vertical force would be the J force. And that J force is a sine relationship. Sine of 50, sine of 32. But the resultant force here is pulling down at 100. And so if I want to find these forces, that it comes out of this kind of a relationship. Again, if I was to write this a slightly different way, T1, the total tension force on this is the I component plus the J component. And the total tension on T2 is the cosine of this plus the sine of this. And ultimately, once I find these I's and J's, like I can build out my T1, T2, but I don't have these forces to set them equal to. And that's why I'm kind of grabbing these forces individually to build their own equations. And what I'll do is I'll throw in some dummy variables. I'll call this equation x, I'll call this equation y. So this component of y plus this component of y makes the total y. This component of x plus this component of x makes the total x. And I know that's probably not your favorite, but if you think about it, it simplifies this equation. And if you remember, these are just decimals. So now I have a simple system of equation that I can solve via decimals. Yeah, I can do I can do substitution and things like that, and it'll definitely turn out that way. I can also use decimals to solve it out that way. But that's another way to kind of relate these components and these vectors and these directions to systems of equation and things that we've done before. I'll leave again this one for you to solve. It's not the end all be all, but I just wanted to relate. It's a very classic problem, and I wanted to relate a little bit of what we've been doing in our review to what we are doing in our vectors.